Okay, our next topic is exact area and the definite integral. So in the previous video, we actually learned how to do something. We didn't have the vocabulary yet, but it was something called an indefinite integral. We were doing things like this. I would give you a function f. I'd say, please integrate it. And you would get the antiderivative, capital F. Always add your constant of integration. And we talked about, like for x cubed, the antiderivative is 1/4 x to the fourth plus c. That created a family of functions. So right here, the answer for an indefinite integral is another function itself. That's as opposed to what we're going to do today, definite integrals. And these are going to have little numbers on top of that elongated s. So we might have something like integrate x cubed with respect to x from 0 to 1. So we have little numbers, which are called limits of integration. Lower limit of integration is a usually, and b is your upper limit of integration. But again, they're numbers, constants. You want to integrate some function x cubed over this range, x goes from 0 to x equals 1. When you have limits of integration, you have a definite integral. And your answer, instead of being like a family of functions, an antiderivative of capital F, it will actually be another number itself. Like this answer right here to this function might be 10. And that number is going to represent an exact area. We'll get to that in a moment. But make sure you see the difference between these two types of integrals. Indefinite integrals, your answer is a function. Definite integrals, your answer is a number. Now I'll explain this notation in a bit. Okay, now I said that we were going to relate these integrals and these antiderivatives to stuff from chapter 1, where we were using Riemann sums, dividing a region, irregular region, into a bunch of skinny little rectangles, summing up the area of each of those rectangles, and we would get an approximate area. Well, now we're going to make that approximation exact. And notice this top line, that is a Riemann sum. So delta x was the width of each one of those rectangles. So maybe your function, well, let's actually do the x cubed function maybe. Y equals x cubed comes through here. So if I want the area from the function to the x-axis, this shaded region in here, we did that with a Riemann sum by dividing the region from 0 to 1 into, say, 4 regions, 1/2, 1/4, 3/4. We would go up to the function, either make a left, right, mid, trap, Simpson's rule, however, what level of precision we wanted. And we said if we let, in this case, when you did n equals 4, the delta x was 1/4 each time. That was the width of each rectangle. If I'm doing the right rule, it would look like this. So just review a bit. Clearly, it would be an overestimate. That estimate would improve as we increased n, the number of rectangles, which was the same as shrinking delta x, the width of each one of those. Well, what if I could actually make infinitely many rectangles in there? So I'd be multiplying my widths times the heights of n rectangles, but I'd let n go to infinity. So I'd squeeze as many as I could. Well, it's just a concept because you can't actually do that, right? But the idea of what if you could, the hypothetical thinking, what if you could make n go to infinity, which is making delta x go to 0, what would happen? It turns out, obviously theoretically in your mind, you should understand that that will be an exact area, right? If I just keep making these smaller and smaller, my approximation improves. If I could do it to infinity, it would be an exact area. So no longer an approximation. If I can take a limit as n goes to infinity of this Riemann sum, I get an exact area. Well, here's what's so magical about antiderivatives and integrals. The things that we're doing over here, that is exactly the same as integrating the function. Here, the function's x cubed. Integrate that function, in this case, from 0 to 1. That's our picture here. And when you do it, get the antiderivative of that and evaluate it at these limits of integration, you will get an exact area. So we can use antiderivatives to get exact areas. We don't need to do Riemann sums and take a limit as n goes to infinity. We can just jump straight to sort of the final answer, the easiest shortcut way of doing it. That all that stuff from chapter 1 helped us get approximations, and we can improve those approximations, but we don't need to do all that tedious work. We can just jump straight to the antiderivative. We can use the integral to get exact areas. Okay, but I haven't told you a little bit about these A's and B's. How are we actually going to do that? So let's get rid of our approximations over here. Go back to the original picture. We want the area of the shaded region from the function y equals x cubed to the x-axis. To get that shaded region, we need to do this antiderivative. Well, the first thing though, this is a definite integral. I haven't told you how to do definite integrals yet. We know how to do indefinite integrals. So for the moment, ignore the limits of integration. Pretend it actually is the easier case, the one we already did, where it's an indefinite integral. What is the antiderivative of x cubed? That's a power function, so you take it up a power over the power. So we will get 1/4 x to the 4th. Normally you'd have the plus c, but for definite integrals, we don't need that. And here's why. We're going to put these brackets, and we're going to remind ourselves that our lower limit was 0, x equals 0. The upper one was x equals 1. We know those are x limits because we're integrating with respect to x. That dx helps us remember that. And then here's what is called the fundamental theorem of calculus. So fundamental, you can relate. And again, this is going to give us, this number is an exact area. And that exact area is just taken by getting your antiderivative and evaluating it at the upper limit minus what happens at the lower limit. So I will be taking 1 and plugging it into for x. So I'll have 1/4 times 1 to the 4th minus 1/4 times 0 to the 4th. And again, that's evaluating your antiderivative at the upper limit of 1 minus what happens at the lower limit of 0. Go ahead and do the arithmetic there. That's just 1/4 minus 0 is 1/4. And that tells us then that this exact area, this area is exactly 1/4. If you wanted to check that, you could try with Riemann sums. You could use one of the tech tools where you set the Riemann sum with the mid rule to do n equals 100. And you'll see that your n equals 100 is getting closer to 0.25, n equals 1,000, even closer, n equals 10,000, even closer. But rather than have to do those calculations or use a tech tool, we can jump straight to the exact area. So you can intuitively see it with the Riemann sums converging, or we can go straight to the antiderivative, the fundamental theorem of calculus, and we get an exact area. Okay, so let me erase the board and put up some more problems. Okay, let's look at these 3 problems. We want to find the antiderivative. We want to integrate square root of x from 0 to 3. This is a definite integral. Third problem, clearly a definite integral. The second problem here, it's written in words, but we could have written just as compactly as these other ones by saying integrate the function x to the 1.5 minus 2x plus 4 with respect to x when x ranges from -1 to 1. Okay, so that statement in English is the same as this compact mathematical statement. So all 3 of these are definite integrals, means when we're done, we'll have a number as our final answer. That number will represent an exact area, and that exact area has a picture. So a good way to check your work and to understand what's happening is to start with a picture. Every definite integral has a picture that goes with it. So let's do that. Let's draw the picture for the first one. The square root function looks like this. If you don't remember, pause the video, get out your tech tool, your TI calculator, go to Google, go to Wolfram Alpha, go to Desmos. The square root function is like that. And then we want to x ranges, x equals 0, 1, 2, 3. We want the area then from the function to the x-axis. That's a key phrase. Always remember you're going from the function to the x-axis. That'll become really important when our function lives maybe something like this. Maybe we wanted the area from A to B. You go from y equals f of x to the x-axis, from the function to the x-axis, from x equals a to x equals b. Okay, so we would be getting that shaded region. Okay, but ours is this function here, the simpler one. And we want to get the exact area of that. We know ways to get approximate areas. That's all the things from chapter 1. Pause the video, review that if you want. Review using a tech tool to get those and make those approximations for really big ends like n equal 100 and see just how close your approximation is. But we're going to do it a much shorter way and get it exactly. And so the shorter way says I need to get the antiderivative first. I pretend that this is just an indefinite integral. These limits aren't here. This is really, maybe one thing first, square root of x is x to the 1/2. That'll help us remember that it is a power function. We take it up a power, so we'll have x to the 3/2, which is 1.5, if you'd like to put it that way, divided by 1.5. And then we'll evaluate it. Don't forget the limits of integration. We haven't actually done that. We have done the integration, so we can get rid of the elongated s sign. We have integrated using the power rule for integration. We're at this point. Now we need to plug in at the upper limit minus the lower limit. So always the upper limit first. So we'll have 3 to the 1.5 divided by 1.5 minus 0 to the 1.5 divided by 1.5. This whole back term goes away. We just have 3 to the 1.5 divided by 1.5. That's a decimal you can get on your calculator. I'll use a tech tool so we can get a precise answer here. So I'm just going to put it into Google. And we get 3.46. So and you can get as many decimal places of accuracy as you need and compare that with your approximate answers. We can add 4106 016. Right. So many more digits we can add because we can give any level of precision now. Maybe let's jump down to the bottom one here. We want to integrate this. This also is a definite integral. We will get an exact area. Let's think about the picture that goes with this one. So it's a parabola, second degree. So it's probably a parabola opening down because of the negative sign. So we kind of have a vague idea what it looks like, but let's just to practice use our tech tool. Okay, so we'll go to Desmos, use its graphing calculator, enter our function is y equals 1 plus 2x minus 3x squared. Okay, so it is this parabola opening down. We want to look at from 0 to 2. So it's going to be this part and this part. So let me put it on the board and then we'll shade the region of interest. So we have something like this, roughly. We want to go from the function, this parabola, from 0, the function to the x-axis, and then all the way over to x equals 2, which is this line here. So we'll be shading. That's what we'll be computing. We can go ahead and do our definite integral by treating it like an indefinite integral first. Imagine these aren't here. Get our antiderivatives. So just a couple power rules. We'll have x plus 2x squared over 2, which is just x squared, minus 3x cubed over 3, which is just x cubed. We're going to evaluate that from 0 to 2. We plug in at the upper limit first, minus the lower limit. The lower limit is particularly nice, just zeros. So we really just have to focus on that upper limit. When we plug in 2 for x, we get 2 plus 4 is 6 minus 8 is -2. All right, well, let's think about that one for a moment. What does that mean for us? And does that make sense, right? I mean, -2, can we have a minus area? Well, the reason we get a minus area is because there was more, my picture's a little skewed here, it's really coming way down. It's quite a bit more down there, but there was more below the x-axis. When you compute these areas, you'll be getting negatives, because think about the Riemann sums. The heights of those rectangles would have been negatives because they lie below the x-axis. So this part evaluates to a negative. This part is above the x-axis, so this evaluates to a positive. There's more negative than positive, and so it's like taking out, you can sort of imagine this upper blob, if it was flipped over and turned here, that's sort of taken away. This red, that red matches this one here, and then you still have some black that's negative that's left. And so this is what, when you compute a definite integral and there's some above the x-axis, some below the x-axis, you're getting a net area. So it's important, right? This picture is showing a net area. But what if you're actually like going to Lowe's or Home Depot and you need to get enough gravel to put in something in your yard that has this sort of shape? Well, you're not getting negative. Negative doesn't make sense. If you want a physical area, then you have to do something different. So if you wanted to do a physical area, we'd have to take this part that's above the x-axis, that's already positive, and then we'd subtract or take the absolute value of the part that's below, because that's negative. You can subtract the negative and you get a positive. So you'd be adding 2 positives. Or you can think of it as taking the absolute value of this part that's down here. Now you're getting 2 positives and adding them together. So you'd actually have to compute 2 integrals. So one from 0 to whatever this point is, which let's just put that in here and call it B right now. So to get the physical area, we change this problem. And we'd say we'd need to go from 0 to B. Again, that's that point on the x-axis. It's the x-intercept right here. Plus, or sorry, what do you do? Plus the absolute value of the integral from B to 2 of that same function. I should say dx. That is your physical area. You're getting the part above the x-axis, and then you're taking the absolute value, or negating the negative part, the part that is below. Okay, well, how do you get this B? If we went back to Desmos, you could estimate it. You can pick that point right there. Oh, that's 1, 0. We don't even have to estimate, it looks precise. So this B would now be replaced with a 1. The other way to get it is to solve for the x-intercept of the function. This function right here, this parabola, you solve for the x-intercept. That happens when y is 0. So you're basically setting this equation to 0 and solving for x. You'll see there are 2 x-intercepts. The one we want was the positive one over here when B is 1. Okay, so make sure you know the distinction between physical and net area. And let's work one more problem here, the second one. Okay, every definite integral has a picture that goes with it. So let's start there. Not quite a parabola, so let's go back to Desmos and see what this function looks like. X to the 1.5 minus 2x plus 4. And I should probably modify this a little bit because minus 1 doesn't make sense. Let's say we want to go from 0 to 1. Right, so this picture would say we want the region from this sort of Nike swoosh sign. This function looks kind of like this. Up here at 4, dips down a bit, rises up. That is f of x equals x to the 1.5 minus 2x plus 4. And we want to go, the limits of integration are from 0 to 1. So we would be going from the red down to the x-axis, just over this region here. Let's maybe write it on here. All right, so this is the picture that goes with this integral. We will be getting the exact area of that region. You can guess right here that it should be a little less than 4, right? Because a width of 1, height of 4, not quite that, so maybe 3-ish around there. So let's go ahead and do this integration. The integration means we need to treat it as an indefinite integral first, get the antiderivative of each piece. So this will be x to the 2/5 divided by 2/5, I'm sorry, 2.5, x to the 2.5 divided by 2.5 minus 2 times x squared over 2, which is just a minus x squared, plus a 4x. That is the antiderivative. If you weren't sure, you would take the derivative of your antiderivative, get the integrand back. Okay, we did it right. You don't need the plus c of the constant of integration because it is a definite integral. Our answer should be a number. Now we're going to go ahead and handle those limits of integration. You always plug in at the upper limit minus the lower limit. So when we plug in 1 for x, we'll get 1 to the 2.5 is 1. So 1 over 2.5 for the first term, minus 1 plus 4, minus what happens at the lower limit, 0, 0, 0, 0. So let's see what this decimal is. Use a tech tool. You should pull out your calculator. And we want to calculate 1 divided by 2.5 minus 1 plus 4. 3.4. That is your exact area. We kind of had a guess it would be a little less than 4, a little above 3. Okay, so summary, definite integrals as opposed to indefinite. We have limits of integration. When we compute them, we get a number which represents an exact area. It is the limit as n approaches infinity of the Riemann sum. We calculate it. We actually do this by doing an antiderivative and evaluating it at the upper limit minus what happens at the lower limit. Every definite integral comes with a image in your head, a picture of what you're computing, right? These different ones. Last thing, physical area versus net area. If you want a physical area and some of your surface lies below the x-axis, you need to split this as the integral from a to whatever this point c is, minus the integral from c to d, because you're negating that negative, plus the integral from d to e, minus the integral from e to b, right? So you have to keep negating the negatives to turn them into positive to make physical area. If you want a net area, you just go ahead and do one integral from a to b of your function. All right, have fun practicing those.